Hello and welcome to Lecture 9 for the course ECE 257A, Fault-Tolerant Computing. This lecture covers chapters 13 and 15 in the textbook. Chapter 13 is entitled Error Detection, where we learn about error detecting codes. And chapter 15 is entitled Self-Checking Modules, which is one important application of error detecting codes. The next lecture 10, will cover chapters 14 and 16, dealing with error correction, error correcting codes, and a very important application of such codes, redundant disk arrays. Okay, so let's start with chapter 13, error detection. So, let's start with something that we already know about, duplication as a method of checking errors. So if you want to compute the function f of x, you may decide to implement two circuits, or use two copies of a circuit computing f of x, provide x to both copies, and these two outputs should be identical under normal condition. If they're identical, then this XOR output will be 0, and we can use the output from the top copy. If they're not identical, if they differ, so this does not have to be a single bit. If it's a single bit result, it's just a simple XOR gate. And if these are, say, words, then you XOR all the bits, and you expect to get all zeros. In other words, they should match in all the bits. So if they disagree, if the two outputs are not the same, then this XOR circuit will signal that there's an error and you just don't use the output. So this is a way for error detection. Once you detect the error, you don't know which of the two outputs is the correct one. So you can't correct the error, but you're aware of the existence of error. However, this method of error detection has a very high redundancy, 100%, not even counting this comparison circuit XOR, which is not very complex compared to the two copies. It's 100% redundancy. So the question is, can we do error detection using less redundancy than 100%? And preferably an order of magnitude less, in other words, 10%, 15% of that order. And the answer is yes, and we can use error detecting codes for this purpose. So with this duplication, the encoding process, so we have a code where a word X is represented as XX, two copies of X. Okay, these are the two copies. Encoding is basically a simple fan-out, doesn't involve any computation. And decoding is also simple. If you do use the output, that output always comes from this module. So those are trivial operations. So we will see that encoding and decoding in general for codes is non-trivial. It involves complexity in terms of circuitry used and also a time delay. So that's basically the price we pay for reducing this redundancy below 100%. Okay, one variation on this duplication is called two-rail encoding. That's basically, instead of using XX as the encoding of X, we use X bar. In other words, X and the complement, bitwise complement of X. We still have 100% redundancy. For example, 0 is represented as 0, 1, 1 is represented as 1, 0. It detects any error in one version like duplication does, but it has the additional advantage of detecting all unidirectional errors. In other words, if all the errors in one of these versions is in the same direction, then the error will be detected. So now this is the encoding. It's basically complementing the input X to find a second version. And then the second circuit, instead of computing f of x, it computes f bar of x, the complement of the function. And therefore, normally we expect the two outputs of these blocks to be complementary. Therefore, we use an XNOR as the error detector. So we gain a little bit of advantage over straight duplication by using two-rail encoding. And then we can implement two-rail logic where if you have a signal T1, C1, this is the true part of the true form of the signal, this is the complement form. And T2, C2, a second signal. If you want to AND those two signals together, you basically AND the true parts and OR complement part. So you still get a two-rail signal, which is the logical AND of these two. So you basically have twice as many signals, and you also have twice as many gates because instead of an AND, you use an AND and an OR. OR is similar. NOT is very simple because to complement the signal, you just switch the two bits. Okay, use the true part as the complement part and the complement part as the true part. That inverts the signal. Next, OR similarly roughly doubles in complexity. Okay, a very important notion in studying codes, whether error detecting codes, which I do in this lecture, or error correcting codes, which I'll do in lecture 10, is the notion of Hamming distance. Hamming distance is defined as the number of positions in which two-bit vectors differ. So imagine two bit vectors of the same length, and then compare them bitwise. The number of positions in which they differ is called their Hamming distance. And basically, to be able to detect a single bit error in our data, the code we use must have at least a distance of 2. In other words, any two code words, any two code vectors that we take from the code should have a distance, Hamming distance of 2. So here is a 2 out of 5 code. This was used in the old days, and is sometimes still used, to encode decimal digits, because when you use 2 out of 5 code, in other words, there are 2 ones, there are 5 bits in the code, and each code word has 2 ones. It's obvious that the distance between code words is at least 2, because if this one has 2 ones, and this one has 2 ones, and the 2 ones are not in exactly the same places, then there will be 2 bits that are different. So in this first example, 1 here has 0, the next code word, and 0 here has 1, so distance 2. And distance 2 is sufficient to detect single bit errors. Okay, so here is the notion represented graphically. So if I have a code word this green circle in the middle, all the words that are distance 1 from it are here, okay? So if I take this code word at the top, there are 5 words that are distance 1 from it, okay? I can change this one to 0. I can change this one to 0, that's the second. I can change this 0 to 1, this 0 to 1, this 0 to 1. There are 5 ways in which I can form a word that is distance 1 away from this, okay? So that circle represents all of those words that are distance 1 from this code. And the next circle out in this diagram are distance 2. Okay, so if a code has distance 2, it means that if this is a code word, there should be no code word on this circle. There can be code words on this circle because they're distance 2 away from this one. Of course, those code words on this circle should be distance 2 away from each other as well. Okay? So this basically explains why a single error can be detected, because if I take this correct code word and change 1 bit in that code word due to error, then I get one of the words on this circle. And none of those is a valid code word, therefore I'm able to detect that single bit error. On the other hand, if I have 2-bit errors, then I can get a word on this second circle, which may be a valid code word. So let's take an example. If I change this 1 to 0 and this 0 to 1, that's an example of a double bit error. Then this code word is converted to another valid code word, and therefore the error goes undetected. Okay. More generally, so distance 2, Hamming distance 2, I sometimes say just distance rather than Hamming distance, because in the context of coding, distance means Hamming distance. If I have a distance of 2, then I can detect single errors, and such a code is known as a single error detecting code. If I have a distance of 3, I can detect double errors. So imagine that the nearest code word to this one is on this third circle. There's no valid code word on the first circle, distance 1, and none on the second circle, distance 2. The closest one is distance 3. Therefore, if I have up to 2 errors, it's impossible to convert a valid code word to another valid code. And more generally speaking, if you have distance d, you can detect d minus 1 errors. Now, if your distance is 3, you have the option of detecting 2 errors. If you use the code as an error detecting code, you can detect 2 errors, or you can correct 1 error. Okay, so here is the justification. This is a code word, and the nearest code word to it is on this circle. So if you have a change in this code word, you move to this circle. If you have a change in this code word, you move to this circle. And therefore, the 2 erroneous words will be distinct. In other words, there's never a possibility to confuse this code word for this code word when you have a single error. So if you have a single error and you go here, you can go back, you can correct that error. But if you go from here to here, you can go back, because no other code word will map to here as a result of a single error. So distance 3, you can correct 1 or detect 2. Either one or the other, you can't do both. If the distance is 4, you can do both. You can correct 1 error and detect 2 errors. So here is a distance, for example. This is a code word. This is a code word. If you have a single error, you move here, or you move here, and that's correctable. If you have a double error, there's a chance that you get from both of these code words to the same erroneous word that happens to be different in 2 bits from both of those. And therefore, you can detect the error, but there's no way to correct it. If you have 5, you can correct 2 errors, or you can detect 4 errors, or you can use a combination, correct 1 error and detect 3 errors. So these have names. SecDet means single error correcting, double error detecting. Sec3ED means single error correcting, triple error detecting. Okay, now generally speaking, if the distance is h, then you can detect D errors and correct C errors if this relationship holds. So double error detecting, single error correcting requires a distance of 4. Okay, single error correcting, triple error detecting, 1 plus 3 plus 1 requires a distance of 5. So this is a useful formula to know. Of course, D must be greater than or equal to C. It doesn't make sense to say single error detecting and double error correcting. That doesn't make sense. Okay, in order to discuss errors, we need to classify them into categories and have models for them. Models basically uh, uh, schemes that allow us to sort of deduce how these errors can occur based on physical properties of our information processing system. The goal of error tolerance methods is to allow uninterrupted operation despite presence of certain errors. Okay, of course, uninterrupted occurs when we have error correction. If we have error detection, we just know that an error occurred and we can't continue the computation. We have to basically go back and redo the computation, restart. So error model is relationship between errors and faults or other causes of errors. Errors are detected, corrected through redundant representations, basically data plus code checkers, or through some reasonableness checks. So for example, activity monitoring and so on. So for example, you don't always need to have codes to detect errors. For example, if a data comes in and you're processing that data that represents the height of a person in feet, and the data is 12, then a reasonableness check basically detects the error, assuming that there's nobody in the world who is 12 foot tall. So some reasonableness checks based on prior knowledge or domain knowledge about the data can allow us to detect errors without any encoding. But those are exceptions. Usually for normal data that we process, we need encoding. Okay, errors can be single or multiple according to the number of bits affected, single bit or multiple bits. Of course, multiple errors can be double errors, triple errors, quadruple errors, and so on. It can be of type inversion or erasure. Inversion means a 1 being changed to 0 or 0 being changed to 1. That's an inversion error. Erasure error is when a 0 or a 1 basically disappears. So you know that there was a symbol here, but you don't know whether it was 0 or 1. It was erased. An example of this would be if you receive a voltage level that is not between 0 and 1 levels, and you can't tell whether it was 0 or 1 with certainty. Okay, you may be able to tell that this is more likely to be 1 than 0, but if you want certainty, those intermediate voltage levels are basically erasure errors. Random or correlated. Random is when multiple bits are changed randomly, independently, and correlated is when multiple bits change as a result of a common cause. An example of correlated errors are byte errors, an error that affects multiple bits in a byte, and burst errors. Burst is when an error affects multiple adjacent bits. So a burst of length 5 bits, for example, in a 32-bit word means that that burst can affect 5 consecutive bits. And these are common, for example, when you do bit serial transmission, when you're sending bits of your data one at a time. And if something goes wrong with the communication channel, and that thing lasts for the duration of 5-bit transmissions, then it can cause a 5-bit burst error. They can be symmetric or asymmetric. Symmetric means 0 to 1 inversions and 1 to 0 inversions are equally or almost equally likely. Asymmetric means that one of those is much more likely, or in some cases, your errors are unidirectional. In other words, your received word or processed word has multiple errors, but you know that either multiple zeros have changed to 1 or multiple ones have changed to zeros, but not both at the same time. So these unidirectional errors are typically easier to detect because of this restriction. Okay, for non-binary code, we usually discuss binary codes, but we also have non-binary codes, in which case an error means substitution of one symbol for another symbol rather than inversion. Okay, so for example, if you have a decimal code and each code symbol is a digit 0 through 9, then if a 5 changes to 8, that's a substitution error. So for bits, we talk about inversion errors. For non-bits or general symbols, we talk about substitution error. Okay, so the transposition error I'll discuss in the context of an example. Now, errors are permanent by nature. We talk about transient faults. Faults can be transient. A signal can momentarily change from 0 to 1. But an error is typically not transient. Error is when you store something incorrect in a flip-flop or in a register. So it's by nature permanent. You have to go back and change it to the correct value. It doesn't change on its own. Whereas a transient fault can basically disappear on its own in a few microseconds or milliseconds, depending on the duration of the transient. So in our terminology, the terminology that we use in this course and I use in my book, there's no such thing as transient error. We have transient faults, but the errors are by nature permanent. Okay, here are some examples of error detection in natural language text. So here I was trying to write the word error. Maybe the printer had some problems, or maybe I'm covering up part of this word. If you look at that word, you can't make it out, probably. You don't know what it is. So this is an error. This is basically an erasure. It has been erased. Okay? As you show more and more of that word, at some point you realize that maybe here or here, that this word is error, even though still you don't have the entire word. There's natural redundancy in natural language text so that you can understand, you can decode these words, even though part of the word is not present. It has been erased. Similarly, you can have letters erased, and then if you know that this is a word from the context, you sort of deduce that this is error. So that's erasure, 2 erasure errors. This is a substitution error where that R has been replaced by Q. Still, you probably can understand that this was meant to be error. So you basically detect, in this case actually correct, that substitution error. And then this is transposition error, where this R and O have switched places. Now, transposition errors are quite common in manual data entry. That's why we'll see in barcodes, for example, they aim to detect transposition error. Because if a supermarket cashier, for example, the scanner doesn't work correctly, and the cashier enters the code manually, it's very common to transpose two symbols, and therefore these are important for that particular application. Okay, application of coding. Coding basically historically was developed in connection with communication channels. So you would send a symbol from the transmitter. The symbol would go over a noisy communication channel and perhaps changes as a result of noise, and you want to be able to detect that something has changed, or maybe corrected, error detecting or correcting codes. Okay. Now, in communication channels, you don't do data processing. You just take a symbol, encode it, and send it, and decode it. Now, in computer application, we have this processing data manipulation step as well. So we have an input, say, coming from memory. We encode it. We send it. This send can be over a communication line or over the bus or whatever. And then we store this in memory. And then when we retrieve it from the memory, we can send it to the location where it's needed. We decode it and send it to the output. If this was just a communication application, this would be the path. But if this is a data processing application, then the decoded value will be manipulated. So two numbers, both of which were encoded, will be decoded, added, and then the sum will be encoded and stored in memory. Notice that during this data manipulation phase, processing, data is unprotected because you remove the redundancy, you decode it. These are just ordinary numbers, not encoded. So if something goes wrong here and a bit changes, you won't be able to detect it. We'll see later that there are codes that you don't have to decode before adding numbers or multiplying numbers. And those are good because data remains protected through this phase as well. So for example, we will see arithmetic code, such as representing x by 15x, multiply x by 15. This is a particular product code. Okay, so y is also represented as 15y. And if you want to add these two numbers, you add 15x to 15y, and you get 15 times the sum, and that's the encoded version of the sum. So you don't have to remove the encoding, and therefore the data remains protected. Okay, so this diagram is a high-level view of the concept of error detecting codes. So we have a data space where there are data words. We have data words that we want to encode. Let's say, for the sake of simplicity, these are 32-bit numbers. Our data words are 32-bit numbers. We encode these data words into longer words. We introduce redundancy. So instead of 32, it may be 40 bits. So these are code words. I added 8 bits of redundancy to protect these data words against changes. Okay, now what code that I use we'll discuss later, but for now, just assume there's some suitable code that makes these data words, takes 32-bit data words and turns them into 40-bit code words. And then that 40-bit code word can be decoded, and from it we can generate the original data. And this relationship is often one-to-one. There's a one-to-one relationship between data words and code, although it doesn't have to be one-to-one. For example, a particular data word can have 2 code words. Going back, each code word must go to a unique data word because otherwise we won't be able to decode it. But it's possible to have 2 different code words for one data word. Usually we don't, but theoretically it's possible. Okay, now these code words have a particular distance from each other so that if, say, a bit in this code word changes, it never changes to another code word. It changes to a non-code word. So the space of words, the code space here, is divided into 2 parts. The set of code words, valid representations, and the set of non-code words, invalid representation, representing errors. Okay? So this code word and this code word, by changing various bits, may both go to this error word. That's okay, that's allowed. We just can't correct the error because if both of these can generate this erroneous non-code word, then I don't know which one was the correct data. On the other hand, if this relationship is also one-to-one, then, like this case, then if this is generated, and assuming this non-code word is not generated by any other code word, I can make correction. So in order to make corrections, I should not have multiple code words mapping into the same non-code word. Okay, the simplest possible error detecting code is the parity check code. Okay, you've probably been exposed to this many times before. If I have a code word, the blue bits, I attach a parity check bit to it in order to make the overall parity even. In this example, I'm opting for even parity. I could do odd parity too. So because there are 3 ones in the code word, in the data word, I add a 1 to make the number even. Now, if any bit in this word, coded word, changes, that 0 changes to 1, it violates the parity and therefore I can detect a change. However, if 2 bits change, for example, this 0 changes to 1 and one of the 1s changes to 0, parity will not be violated, therefore double errors are not detected. So this is a very common code that is used. There's very low redundancy. In other words, you can have 32 data bits and just 1 parity bit. But also it provides very limited protection. If you have 32 data bits, chances of having more than 1 bit error increases. And therefore this single parity bit can provide only limited protection. Okay, so in order to evaluate error detecting codes, we examine several features of the code. For example, redundancy. If we have k data bits encoded in n bits, in other words, we are adding r redundant bits, then redundancy is r over k. R extra bits are used to encode k data bits. That's the redundancy. Of course, we aim to make redundancy as low as possible if we can. Encoding, how difficult is it to encode, both in terms of circuit complexity for the encoder? We'll see examples of encoders and decoders later. And also in terms of the amount of time needed, because if you look at that path where data is encoded and then transmitted and then decoded, the latency of encoding and decoding is added to the overall latency. Therefore, we prefer codes that are fast in terms of encoding and decoding, and also require simple circuitry for encoding and decoding. Simple because it limits the cost and also the power consumption. Okay, capability of the code. What types of errors is it capable of detecting? The greater the detection capability, usually we need more redundancy. Okay, the more the detection capability, the more redundancy. Okay, examples of code detection capabilities are single error detecting, single error correcting, double error detecting, B-bit burst error detecting, byte error detecting, unidirectional error detecting, and so on. Okay, and closure, of course, is a good property to have. Closure means that arithmetic and other operations can be done directly on code words. In other words, the code is closed under the types of operations that we want to perform. This is not a common property of codes, okay? We'll discuss a special category of codes called arithmetic error detecting codes. But those are not very commonly used. So usually this particular property is not at issue. Okay, let's consider a particular class of codes called checksum codes, exemplified by the 12-digit UPCA universal product code. So this is basically the 12-digit universal product code up to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 digits, sorry. And then a 12th check digit has been added. So the 12th digit includes that check digit. Okay, and the rule for adding the check digit I can tell you through an example. Sum the odd index, so index these digits, 1, 2, 3, and so on. The red indices are odd indices. The blue indices are even indices. So the process for determining this check digit goes like this. Sum odd index digits. So add 0 to 6 to 5 to 0 and so on. And you get 14. Multiply by 3. So this is the basically encoding process. Whatever sum you get here, 14, multiply by 3, you get 42. Now add to this 42 even index digit. Even index digit in this example are 3, 0, 0, 9, and so on. You get 58. Find the next multiple of 10 after this number, which is 60, and subtract that number from it. You get 2. So that's the check digit that you put there. Okay. Now, basically what you're doing, you are making, now that location is actually an even index location. It's location 12, okay? So you give odd index location a weight of 3. You give the even index location a weight of 1. And therefore, if you do this calculation and then simply add the check digit, you get a multiple of 10. And that's basically a sign that your code is okay. There's no error in it. Okay? So the process of error detection is do this calculation, but include also the check digit, which is an even index digit, so add 2 to this. So you get 60, which is a multiple of 10, and it says that there's no error. If it's not a multiple of 10, then you have an error. Now this particular code detects all single-digit errors. If one of those digits changes, let's say this 6 changes to 4. That's an odd index digit. 6 changing to 4 reduces its value by 2. 3 times 2 is 6. So it will reduce the sum by 6. And therefore, the sum will no longer be a multiple of 10. And you detect that error. So any single digit error, whether you increase the value of a digit or decrease the value of a digit. Okay, so for example, if this barcode is not easily readable and cashier mistakes this 6 for 0 maybe, then it will be detected. Or if the scanning device, let's say this is scratched and the scanning device cannot read it correctly, then the error will be detected. It detects most, but not all transposition errors. So let's take an example. Let's say this 1 and 4 being transposed. So the normal sum would be 1 times 3, because this is an odd position, plus 4, which is 7. When you transpose it, it will be 4 times 3, 12, plus 1, 13. And therefore, the sum will not be a multiple of 10. There are exceptions, though, and I leave that as an exercise for you to determine what types of transposition errors are not detected by this code. And that's basically a compromise. In order to manage with just a single redundant digit, they had to compromise and allow those few transposition errors to go undetected. Of course, if we add more redundancy, we can detect those. Okay, so generally speaking, checksum codes are like this. You have a data vector. You encode the data by attaching the checksum xn plus 1, the last symbol, such that summation of all the digits, each multiplied by its corresponding weight, is 0 modulo some checksum constant. Okay, so for example, the UPC-A code on the previous slide has these weights. Odd index positions of weight 3, even index positions of weight 1, and the check constant is 10. You do modulo 10 checking. Okay, so these weights are up to me to assign. I don't have to assign only 3s and 1s. If I can show that other weights, introduce desirable properties for my code, I can use other weights. Okay, such a checksum code detects all errors that add an error magnitude that is not a multiple of A. If the error magnitude, if what is added to that checksum is a multiple of A, then the error goes undetected. And just for your information, this is not really relevant to our discussion of the code, but these barcodes, this 3 or this 6, actually consist of 7 bars, dark or light bars. And so, these narrow lines are just one of those. Narrow gaps are just one of those. Then you have this maybe 3 bars like that. So 4 that you see here consist of a bar, a blank, then 3 bars, 3 black bars, and then 2 white bars. So that's basically so that the scanner has some error detection capability. If these bars are not completely formed on the label, it can still make sense of the digits. Okay, weight-based and burger codes are the subject of the next section. And so this is a weight-based code. This is weight 2. In other words, code words are 5 bits long, and every word in this code has a weight of 2, meaning it has 2 ones. Okay, so this one is capable of detecting all unidirectional codes, because even if 3 zeros are changed to ones, the weight changes. If one or both of these ones change to 0, the weight changes, therefore you can detect it. However, if this one changes to 0 and this 0 changes to 1, the weight remains the same, so it does not detect bidirectional errors. Unidirectional errors in any number of bits are detected. Of course, a single bit error is always unidirectional, right? If you have a single bit error, either a 1 changes to 0 or a 0 changes to 1. So single bit errors, and in fact all unidirectional errors. Okay. Burger codes were invented by J. Berger, an IBM engineer. I tried to find a photo of him, and to my surprise there was no photo of him on the internet. So I'm going to keep looking and put a photo here. As a way of giving him credit. So J. Berger of IBM defined this code. So you have data words, like 6-bit data words. So these are 64 data words going from 0 to 63. Berger suggested for us to count the number of zeros and attach that as a number as the redundant part. So for example, here I have 6 zeros, and 6 is 110 in binary. Okay, here I have 4 zeros in this code word, and 4 is 100. Okay, why did he decide that it's a good idea to count the number of zeros and add it here? It turns out that this code is unidirectional error detecting, because if zeros change to ones, the number of zeros is decreased here, and zeros changing to 1 here increases the count, and therefore they will not match. So if some zeros in the data part change to ones and some zeros in the check part change to ones, then the count certainly will not match. Whereas if we had counted ones, okay, so we could say, all right, here there are 2 ones here, so this code will be 010. Then if this one changes to 0 and this one changes to 0, a unidirectional error, it will not be detected. So by attaching the count of zeros, you make the code capable of detecting all unidirectional errors. So you need log base 2 of k plus 1 check bits for k data bit. So it's fairly efficient. It's a logarithmic number of bits. The longer the data part, more efficient this code becomes. So if you have a 32-bit data part, a 31-bit, let's say, 31-bit, then log 2 31 plus 1 will be 5 bits. You need only 5 bits. And it becomes even more efficient if the data part becomes longer. Okay, the next category of code, I should mention at this point that codes, and this is true to some extent of all the topics that we consider. So for example, fault detection is by itself a fairly broad topic. and we just basically touched upon some basic ideas in fault detection. Now, error detecting and correcting code is even broader in scope, and in fact, some universities offer a course sequence dealing with error detecting and correcting code. So multiple courses devoted, because there are so many different codes, and there are so many different theories on which code construction is based. So we're going to touch upon some examples to give you a basic feel for why codes work, why they detect or correct errors, and some typical codes, some of the most commonly used codes you'll be exposed to, and some other codes you'll just hear the names, but at least you have the general knowledge to be able to pursue a study of codes if the need arises in the work that you do. So what are cyclic codes? Cyclic codes are codes for which any cyclic shift of a code word produces another code word. So here's an example of a cyclic code. In a cyclic code, we have a k-bit data word. So let's say this is our data word. And k in this example is 7. And this data word is represented by a polynomial. So it's 1 plus x. There's no x squared. Okay, the coefficient of x squared is 0. Plus x to the third. No x to the fourth, no x to the fifth, plus x to the sixth. So this polynomial, in which addition is modulo 2, I'll explain what that means, represents this data. In other words, there's a one-to-one correspondence between data words and polynomials such as this, in which the coefficients are ones or zeros. Okay? Addition is done modulo 2 means if I add x to this polynomial, x plus x becomes 2x, and then 2 modulo 2 is 0. In other words, x plus x cancel each other out. So addition is sort of like subtraction in this modulo 2 operation space. So adding x is like subtracting x to this polynomial. Okay. So a polynomial is a data word is represented by a polynomial. And the code has a generator polynomial of degree r. So here's an example of a generator polynomial, 1 plus x cubed. Okay, r is equal to 3 in this example. Okay, and then encoding is done by multiplying the data polynomial by the generator polynomial. So this is the data polynomial. This is the generator polynomial. We multiply. 1 times 1 is 1. 1 times x is x. 1 times x cubed is x cubed. 1 times x to the 6 is x6. Then we go to x. X times 1 is x. X times x is x squared. X times x cubed is x fourth, and so on. And then we simplify. Basically, this x cancels this x. This x cubed cancels this x cubed. And we get this. So this is the encoded version of that data word. Okay, the polynomial corresponding to this encoded version is 1 plus x squared, 3, 4, 5, 6, plus x seventh, 8, 9, plus x 9. Okay, such a code detects all burst errors of width less than n minus k, or less than r. So because the generator polynomial was of degree 3, so r, or n minus k, is equal to 3, any burst error of size less than 3, in other words, burst errors of size up to 2, will be detected by this code. So now burst errors do not have to be unidirectional. As long as two consecutive bits are affected, one can change from 1 to 0, the other one from 0 to 1, it's still a burst error. Burst means the effect of the error is limited to consecutive locations. Okay. Now cyclic codes that I discussed on the previous page have simple encoding and decoding circuits. I won't try to explain why this works. Basically, the data word comes in one bit at a time, and then it goes through the circuit, and then the encoded word emerges from there. Now, the structure of the circuit is dictated by the generator polynomial, which was x to the 3 plus x plus 1. Okay, so x to the 3, x, and 1 have flip-flops, the three terms that existed in that polynomial. And then you have an XOR gate between these two terms and between this one and output, but not here. So that's the decoder. So it's a simple circuit. Of course, because data must come in bit serially, it can be slow. And this is the decoder. Here the encoded word comes in, goes through the circuit. Again, x cubed plus x plus 1 is the generator polynomial that dictates the structure of the circuit. And then the decoded data emerges from here. So both encoding and decoding are fairly simple, low cost, if done bit serially. We can also have separable cyclic code. Now, the notion of separable codes is very important because the code that we discuss, both the constant weight code and this, not this one, the constant weight code in this slide is not separable. Data, it's redundant, because to encode 10 things, you need only 4 bits. Here we are using 5 bits. But you can't point to one of these bits as being the redundant bit. Data and the check part are intermixed. This is known as a non-separable code. Burger code, on the other hand, is a separable code because the check bits are separate from the data. So this means that decoding is trivial. If I give you this code word, you just look at these 6 bits and that's the data. Decoding is trivial for separable code. So we are interested in seeing whether we have separable cyclic codes. Yes, we do have separable cyclic codes. So I'm going to let the reading of this slide to you. There's one particular way of constructing a separable cyclic code in which when you get the code word after encoding, okay, the data is 1001 in this example, and that 1001 appears here. That's the data part, that's the check part. They're separate from each other. The data maintains its original form, and therefore decoding is trivial. Okay, the next idea is that of arithmetic error detecting codes. These are error detecting codes that are particularly suited to arithmetic operations. First of all, arithmetic operations are different with respect to errors compared with just regular words. In transmission, when you transmit a word over a communication line, and if you have a single bit error, it changes 1 bit, and therefore a single error detecting code, or later we will see also single error correcting code, can deal with that single bit error. Or the communication line may have a burst of errors. In other words, for a particular duration of time, there's noise, and therefore several bits in sequence are affected. So if you have a burst of length 4 bits, affects 4 bits, and if your code is capable of detecting bursts of length 4, then you will be okay. Now in arithmetic circuits, sometimes a single fault or a single error causes a large number of bit flips. So let's take this example. Addition of these two numbers. I'm adding these two numbers, and this is the correct sum. Now when the adder that is adding these two is operating on the 2, carries will be generated. And let's say inside the adder, this carry, which is supposed to be 0, because this position with 2 zeros should generate a carry of 0. Suppose changes to 1 because of fault in the circuit. When that carry changes to 1, it propagates over these 8 bits and changes them to 0. 11 bits. And then it also changes this 0 to 1. So that single fault in the adder circuit causes 12 bit flips in the output. Okay? All these 12 bits have been flipped. And it's unlikely for us to have a code that can detect 12 bit flips. So normal codes really cannot deal with this kind of error that commonly occurs in arithmetic circuit. So what's the solution? Well, the solution is to define the error not by changes in bits. Okay, we don't view these as many errors. We view these as the addition of 2 to the 4 to the correct sum. Okay, so this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2. If I add 2 to the 4 to this correct sum, this word will result. Okay, so a single error in this arithmetic context is an error that changes the value of a word by a power of 2. So here's an example. So the output of that adder here, if you add 2 to the 4 to it, which is equal to 16, it changes to this. So this is a single arithmetic error because a single power of 2 was added to this to get to this. This is an example of a double bit arithmetic error. 2 powers of 2 have been added. One of them has actually been subtracted. So 2 to the 4 has been added and 2 to the 15 has been subtracted. So the error, in this case, the error was plus 16. In this case, the error is minus 32,752. But this error happens to be of a kind that can be written as the sum of 2 powers of 2. And therefore, we call this a double arithmetic error. Now, codes for arithmetic operations, I'll just explain these briefly. We have 2 categories that are widely used. Product, or sometimes called AN codes. When you want to encode n, you multiply it by a constant a. That's where the name AN comes from. And the residue, or a variation of residue code, inverse residue code. In this, if you are given a number n to encode, you attach to it a check part that is the residue or remainder of n when divided by some constant a. So a in both cases is a constant that is given to us as part of the code definition. This is a non-separable code because when you multiply a number by a, then n itself does not appear in the result. This is a separable code because the check part is distinct from the data part. Okay, so let's see some examples of these. For odd A, so let's talk first about product or AN codes. For any odd A, doesn't matter what, 3, 7, 15, all weight 1 arithmetic errors are detected. Okay, that's because a weight 1 arithmetic error is a power of 2, and therefore it will not be divisible by a, and therefore it will be detected. Arithmetic errors of weight greater than or equal to 2 may go undetected. Here is an example. The error 2 to the 15 minus 2 to the 5 is undetectable with a equal to 3 because this number happens to be divisible by 3. Okay, even 11 will not work because this number is also divisible by 11, and 31 will not work. Okay, so basically product codes are for single arithmetic error detection. And to detect error, we check divisibility by a, and then to do arithmetic, before doing arithmetic, there's a version of these product codes which are called low-cost product code, where this constant chosen is a power of 2 minus 1. So for example, 3, or 7, or 15, or 31. The reason this power of 2 minus 1 is a good check value is that multiplication by a becomes shift and add. We need multiplication of by a for encoding. So encoding is done through shift and add rather than through multiplication, which is a slower operation. Division by 2 to the a minus 1 is also simple. Basically, we compute, let's say this is 15. So you're given 15x and you want to find x. Okay, 15x is given, you want to divide by 15 to find x. You observe that 15x is equal to 16x minus x. Okay, 16x minus 15x. Okay, 15x we know, it's given to us. 16x we don't know, but we do know that 16x ends in 4 zeros. So we know the last 4 bits of 16x. We know the last 4 bits of 15x. Therefore, we can compute the last 4 bits of x. And then once we have the last 4 bits of x, we substitute here. We now have the next 4 bits here, and so on. So if we do the operation 4 bits at a time, we can easily divide 15x by 15 without doing an actual division, which is a slow operation. Any unidirectional error with arithmetic weight of at most a minus 1 is detectable by a low-cost product code based on constant a equal to the a minus 1. So again, taking the example of 15, for 15, a is equal to 4. So any unidirectional error with arithmetic weight at most 3 will be detectable by that code. Okay, here are arithmetic operations. Addition is trivial. If you have x coded as ax and y coded as ay, you just simply add them directly and you get the coded version of x plus or minus y. So you don't need to remove, you don't need to decode and then add and then encode, you just do it. For multiplication, if you add the coded version of a by the coded version of x, you get a squared ax, but you want a times ax. So you have to divide by a, but dividing by a can be simple as explained previously. Division is difficult, so I won't even discuss it. Square rooting is difficult. So for those of you who have taken my course on computer arithmetic, you know that residue number systems are great when you do addition and multiplication, but they're awful for other operations, difficult operations. So they are used in applications when you don't have those difficult operations, such as division, square rooting, and so on. A similar thing holds here. This type of code is used when you don't have those difficult operations. Residue code. Here's an example. So let's say A is 15. So you want to compute the modulo 15 residue of some given number n. So let's say this is the number n, 16 bits, and you want the modulo 15 residue. It's very easy to prove that you simply add these chunks of 4 bits modulo 15, because this is weighted 1, this is weighted 16, and 16 is mod 1 mod 15. This is weighted 16 times 16, 256, and 256 is also 1 mod 15. So you just add these together, modulo 15, and you get the checkboard. So it's a pretty simple process. Okay, once you have encoded your operands using residue code, here is how you operate on them and check for errors. So X and its check part, Y and check part come in. X and Y go to the regular arithmetic processor, do addition, multiplication, what have you. The check parts go into the check processor. And if you want to do addition, you add the check parts modulo A. If you want to do multiplication, you multiply the check part. So the check processor is only 4 bits wide. It's much simpler than the main arithmetic processor. So that's the attractiveness of this kind of encoding, because redundancy is much less than 100%. When you compare it to duplication, this is much better. So the checking is done by computing the result, forming its mod A residue, and comparing with the output of this check processor to see if there's any error. If there's no error, then this is the output. Otherwise, you just don't use that output. Okay, so on this slide, I've just listed a bunch of other codes that you may have heard about, but we won't discuss them in this course. First of all, we have codes for erasure errors. Erasure errors are easier to deal with. It's sort of, if you try to compare it to lying, if you talk to somebody and that person does not respond, you get into less trouble than if the person responds but gives you the wrong answer, okay? For erasure error, you just don't know what that particular bit or symbol is, but you don't get misleading information, okay? So erasure errors typically involve less redundancy and are easier to deal with. Codes for byte errors, okay? Because byte is such an important unit of information in computing, we have specially designed codes that detect byte errors. So no matter how many bits in a byte change, the code detects it. And this is reasonable because a byte comes from a register or from some memory location. And if something goes wrong, it's possible that multiple bits in the byte are erroneous, and therefore byte codes are useful. And codes for burst errors. Okay, so let's now go to chapter 15. Okay. Dealing with self-checking module. It's a very interesting concept. Unfortunately, it is not used that much in practice, even though it's a very powerful way of designing circuits, as we will see. It has not found its way into mainstream design techniques. But if you're trying to design fault-tolerant or highly dependable systems, it's a good method to know. So, suppose I'm designing a function unit. It receives some inputs and computes something for me. It doesn't matter what it computes. The self-checking design paradigm does this. It uses encoded inputs instead of just regular inputs. The function unit operates on the encoded input. It generates an encoded output. We design the function unit so that if something goes wrong in the function unit, some gate is stuck at 0 or some wire is disconnected, the types of faults that we expect to occur in the function unit, we design it such that whenever that happens, this output will show an error. So it's encoded. Normally, if the input is correct and the function unit is working correctly, then we get the correct output encoded as a code word. If something goes wrong in the function unit, then we get a non-code word here. Therefore, we use a code checker. And why this has to be self-checking itself, I'll discuss in a minute. So we use a code checker to check on this. If this is a valid code word, then we are okay. If this is a non-code word, then we have detected the problem in the function unit. Now, implicit in this design technique is that the function unit and the checker both cannot be faulty at the same time. This is a reasonable assumption because these are two separate units, and each of them has a very low probability of being faulty to begin with. So both of them being faulty has a very small, it's a tiny probability that we can ignore. Okay, with this assumption, then this scheme basically detects any faults in the function unit. We can also design the function unit such that if an erroneous input comes in, it generates an erroneous output. In other words, if the function unit is working correctly and an erroneous input comes in, then it generates an erroneous output so that we can detect it. So basically, input error under those conditions is propagated to the output so that we can detect it with this checker. So in abstract form, this is what we are really doing. We have an input space, valid inputs, invalid inputs. We have an output space, valid outputs, invalid outputs. They're coded. And then we expect if the function unit is working correctly, if we give it a valid input, it produces a valid output, which is the normal function of that function. If the circuit has some fault phi in it, then the output will be in error space so that we can detect it through here. So this is part of the specification of this function unit. If it's non-faulty, then it generates a correct output. If it's faulty, then it generates this, or we have the option of designing a circuit so that it does produce the correct output. We basically build in some sort of error correction into this. However, under no circumstances should the unit produce a different valid code word. In other words, if something goes wrong here, we don't want, instead of this correct output, to generate another output that is incorrect, but not the, which is valid, it's in code space, but it's not the correct output. Okay, so the circuit has the option of producing the correct output when it's faulty, or producing an incorrect output that can be detected by this code checker. Okay, so we have four possibilities. Both function unit and checker are okay. This is the normal mode of operation. Only function unit is okay. If the function unit is okay and the code checker is faulty, then it may signal an error, even though there's no error. But this is a safe type of fault because we do have the correct output. This one says that it's not correct. We don't use that output, so we're at least safe. So this is a safe mode. It's not very desirable, but it doesn't cause any serious safety problems. If only the checker is okay and the function unit is faulty, and the checker detects the fault in the function unit, this is a detectable error. And the fourth combination, neither function unit nor checker is okay. Okay, this we do not allow. Okay, we do not allow two faulty units at the same time. Okay, we can cascade self-checking units as shown in this diagram. So this is function unit 1, which is self-checking. Its output is checked. Function unit 2, which is self-checking, is checked. Remember I said that we can design function unit 2, let's say, so that if it receives an incorrect input, it generates an incorrect output. If that's the case, if it has been designed for that, I can remove this checker, save some hardware. Okay, so if function unit 2 is of a kind that it translates an input error into an output error, then there's no need to check this here. Of course, I'm still assuming that one unit out of the 3 is faulty. Because if this is faulty and it generates an incorrect output, and this is faulty and does not generate an incorrect output because it's faulty, then we are in trouble. Okay, of course, I can also, for safety reasons, I can include this. If I include this, then I can combine the check signals from the two self-checking checkers and obtain an overall check. So if this one says something is wrong, or this one says something is wrong, then something is wrong in the overall system. So this is combining outputs of multiple checkers using a self-checking circuit. Okay, let me skip this. So how do you combine error signals? Basically, these self-checking checkers are designed so that they have two output lines, and the two output lines are 0, 1 or 1, 0 if everything is okay. And, and they signal error by generating 0, 0 or 1, 1. Why do we need two output lines? Excuse me. We need two output lines because if we have just one output line, and that output line happens to be stuck at 0, and let's say 0 tells us that everything is okay. If that output line is stuck at 0, then it will never detect anything. So by having two output lines and insisting that both output lines assume values 0 and 1. So 0, 1, for some combination of good inputs here, it generates 0, 1. For other combinations, it generates 1, 0. So both of these lines, through normal operation of the checker, assumes the values 0 and 1. So if one of them is stuck, then we will see this pattern. So when it's supposed to be 0, 1, and if this one is stuck at 0, we'll see 0, 0. If it's supposed to be 0, 1, and this one is stuck at 1, we will see 1, 1. Okay, so that's the idea of having at least two output lines for these self-checking checkers. And this particular example circuit that I let you study on your own combines those pair of check signals and generates a single check signal at the output. This is basically logical OR of those two. If this one signals an error or this one signals an error, then this one should signal an error. Okay, so I'm going to skip the rest of this. Now, the notion of totally self-checking design is important because we mentioned that if there is an error, let's say it's stuck at one fault inside the circuit generates this. But we cannot design the circuit to be tolerant of all faults, okay? We basically focus on a class of faults, like single stuck-at faults, and design the circuit to be tolerant of those single stuck-at faults. Now, if the circuit basically makes too many of these corrections, so there is a single stuck-at fault, but that single stuck-at fault does not affect the output because I've designed the circuit to be fault tolerant. Then at some later time, a second fault can develop in the circuit. And now the circuit is not tolerant of two faults, so I run into trouble. So for totally self-checking circuits, not only we insist that the circuit be self-checking, we want it to be self-testing. In other words, we want it to, for some set of inputs, to actually generate this incorrect output so that we can test it. We basically, before a second fault develops, we detect this first fault. Okay? Now remember, if I have a particular stuck fault in the circuit, and the circuit has a bunch of inputs, now the test for that particular fault may not necessarily be one of these code words. The test may be one of these. But these error space inputs are never received during the normal operation of the circuit. Therefore, if the test for a particular fault happens to be in this area, we are in trouble. We want the test to be among the normal circuit inputs, so that during the normal circuit operation, the circuit is tested and the fault is signaled at the output. So such a circuit that is both self-checking and self-testing is called totally self-checking. It's just a term invented many years ago. Okay. And then this is an idea that I introduced many years ago, self-monitoring design. Self-checking designs tend to be very difficult to generate because of the large class of faults that one has to consider. Now, a self-monitoring design is totally self-checking with respect to some small fault class, which is a subset of all the faults that we are interested in. And this small fault class is chosen so that all faults in F develop in time as a sequence of simpler faults, the first of which is in this F init, initial set of faults. For example, these initial set of faults can be single stuck-at faults. This can be a more extensive set of faults. If these extensive faults always develop by first producing a single stuck-at fault and then perhaps later developing into the more complicated fault, and if my circuit is totally self-checking with respect to these, I'll be able to detect that fault before a second or third fault develops and causes trouble. Okay. Now, as I mentioned before, self-checking checkers have to have at least two outputs. A regular checker has just a single bit output, 0 meaning okay, 1 meaning not okay. But as I mentioned, if that output is stuck at 0, then we are in trouble. So this is a regular checker for an odd parity check code. So if I have odd parity among these 5 inputs, this output of this XOR will be 1, and therefore the inverse of that will be 0, and therefore this signals that everything is okay. So odd parity is represented by 0, and even parity is represented by 1. So this is a regular checker. It's not self-checking, because this E can become stuck at 0, and then we can never detect problem in the input. This is like a fire alarm in a room, basically being stuck, running out of a battery, and therefore it will never sound the alarm no matter what happens, okay? So if this line is stuck at 0, this checker never sounds the alarm, so to speak, and we'll never know that something went wrong. So you can do self-checking with 2 outputs. You need at least 2 outputs. So for example, use 0, 1, and 1, 0 as everything is okay, and 0, 0, and 1, 1 as something is wrong. So this is the self-checking checker for the same odd parity code. Now this is interesting because the self-checking checker is simpler in terms of complexity. It uses only 3 gates as opposed to 4. This usually is just the opposite. The self-checking checker tends to be more complex for this example. So basically, we say if the number of ones at the input is odd, then I either have an odd number of ones here and an even number of ones here. So that's 1, 0. Or an odd number of ones here and an even number of ones here. That's 0, 1. In all other cases, we could get 0, 0, or 1, 1, which is a sign of the code not being valid. Okay, I'm going to skip the next few slides. I'll skip the details. I just give you the problem definition and why. So totally self-checking checker for M. So over the years, people have designed totally self-checking checkers for various codes. For M out of 2M codes, there's a design on this slide. There's a different design on this slide. This is due to J.E. Smith. And this one, let's see, I don't remember who did this, but the reference is given at the end of the chapter. So these are 2 particular designs for M out of 2M. So this is a specific type of code for which we have 2 designs for self-checking checker. This is another design strategy that uses 2 out of 4 checkers as building blocks. So if you have already designed 2 out of 4 checkers, you can design 3 out of 6 checker or 4 out of 8 checker using these designs. And for general K out of N code, we don't have a general strategy that directly do that. However, this is always possible, although sometimes it becomes very complex. So if I want to design a 2 out of 5 totally self-checking checker, and 2 out of 5 is not of the form M out of 2M, so I can't use the previous design strategy. I convert the 2 out of 5 code into a 1 out of 10 code using 10 AND gates. So this can be proven to be totally self-checking. Then I can convert the 1 out of 10 code to 3 out of 6 code, which is of the form M out of 2M, using 6 OR gates. And then I can check this using the methods that we previously introduced. And therefore, the sequence of 3 checkers acts as a self-checking 2 out of 5 code checker. Okay. Let me skip this slide. We can also do self-checking sequential circuit design state machines. So this is a state machine with 4 states and 1 input, and these are the next states depending on the input and the current state, and this is the output. So in order to design a self-checking version of this is one strategy. There are other strategies too. I encode the state using, in this case, a 2 out of 4 code, okay, using a constant weight code. So A is encoded as 0011, B as 0101, and so on. And the next states I read from that table and just introduce them here. Input is also 2 rail, encoded as 2 rail. 0 is represented as 01, and 1 as 10. Okay, so if one of the input lines is stuck, I can detect that, okay? And the output is also 2 rail. Now the nice thing about this is that if states are encoded using a k out of n code, in this case 2 out of 4 code, a constant weight code, one can express the next state functions, one for each bit of the next state. So here I need 4 circuits because 4 bits need to be computed based on the current 4 bits and based on the inputs. So there are 4 circuits that need to be designed. These are the excitation circuits or next state circuit. All of these can be implemented via monotonic expressions, meaning without complemented variables. In other words, we use only AND and OR gates in implementing the next state functions. And because we use only AND and OR gate, any unidirectional error will be detectable. Okay, because in an AND gate, if an input changes from 0 to 1, the output can only change from 0 to 1. And if an input changes from 1 to 0, the output can only change from 1 to 0. Similarly for an OR gate. Okay, so these are, AND and OR gate are both monotonic functions. And therefore, this particular sequential circuit will be self-checking with respect to all unidirectional faults. Okay, a whole bunch of practical design strategies can be found in the literature. I have not yet included, I'll include in the final version of the textbook a few examples of these. Designs based on parity codes, designs with residue encoding, FPGA-based designs, some general synthesis rules, and partially self-checking designs. And these are at present not included in the textbook or in the slides. Okay, so there is a little bit of material here, but not much description to make it completely understandable. Okay, I'll complete these discussions in the next version of the textbook. Okay, so let me stop at this point, and this is the end of lecture 9. I will be recording lecture 10 shortly. Bye for now. Stay safe until the next lecture.